Hi, this is Calculus 12, Chapter 2.1. In Chapter 2, we'll be covering limit, and some of what we're going to do is contrived, but really we need to use limits to prove derivatives and integrals. Okay, so here we have a curve, and we also have the curve here, and we want to be able to estimate tangents. And we're going to estimate tangents with secant lines. So tangent is just another word for slope. And tangent will only touch a curve at one spot. So tangent will look something like that. So it'll only touch this spot right there. It could cross at other points, but we're talking about the points that are close. And we can estimate the tangent line with secant lines here. So we have a point 3,9 and 2,4. So we just use a table of values to figure out some points that are close, and these are the points. 1, 1, 1.5, 2.25, and then we have 2, 4, and we have 2.5, 6.25, and 3, 9. The scale here doesn't match the scale here, but understand we're still doing the same thing. Okay, so we can estimate the slope using 2 points. Tangent is approximately f of x2 minus f of x1 over x2 minus x1. And you'll notice that this is rise over run. Okay, that means slope. And we are approximating with secant lines. Okay, and again, a secant line will go through a curve at 2 points. A tangent line only goes through it at 1 point. Okay, so if we're using 1 and 2, we want to estimate the tangent at 2. So we do f of 2 minus f of 1 over 2 minus 1. That gives us 4 minus 1 over 2 minus 1. That's 3 over 1, and that's just 3. Okay, let's use another point, 2, 3. So we look at 2 and 3 here at the table. So f of 3 minus f of 2 over 3 minus 2. So that is 9 minus 4 over 3 minus 2. That's 5 over 1, and that's 5. Okay, it doesn't matter if we use the smaller number first or I use the smaller number second because then we don't have negative signs. Okay, let's take the closer points, 1.5 and 2.25. F of 2 minus f of 1.5. 2 minus 1.5. We get 4 minus 2.25 over 2 minus 1.5. That's 1.75 over 0.5, and we get 3.5. And last, f of 2.5 minus f of 2 over 2.5 minus 2, and we get 6.25 minus 4 over 2.5 minus 2. That's 2.25 over 0.5, and we get 4.5. Okay, so we can take a guess here. If we average these out, we get 4. If we average these out, we get 4. So the slope is looking like it's 4. But the important thing to note here is as we get closer, the x value being 2, we see that we're getting closer to our answer of 4. So we want to get as close as possible to 2 to get our actual value of our slope. So we have something called limit notation. Okay, we're taking the limit as x approaches a, and in this case it would be 2, of our function. And that's going to equal L. Okay, so this is our notation. This is our function. We use function a lot, so I usually abbreviate this Fn. This is just required as part of the notation, signifying that we're doing a limit. This is our variable. This is our objective. So what do we want to get close to? And it's our x value. And this is our limit value. And that's the y value. Okay, so we're looking for a variable getting close to an x value of a function, and we're going to try to find the y value, or the limit value. And the way we say this is the limit as x approaches a of some function is the value L. So using limits for that previous problem, we take the limit as h goes to 0. So we're taking a very small interval. We took a large interval, we took half of that, but now we want to actually take a very small interval. So as h approaches 0. So we want the function plus some little bit minus the function of that x value, our objective, and divided by h. So this looks like limit h approaches 0. Our objective is 0. We want the smallest interval possible. We're interested in the value at 2, our x value. Okay, so we have limit h approaches 0, and this is squaring, and this is a binomial expansion, and you should know your binomial theorem from pre-calc 12. So expanding this, we have h squared. I'm just changing the order to the variable first, plus 4h plus 4. And we're minusing 4 all over h. We can cancel out a positive 4 with a negative 4. Now, normally we go down the page, but it's easier for you to follow along if I go across the page here. That way you can see the whole solution at once. So now we're left with h squared plus 4h over h. We need our h approaches 0 here. And now we can cancel an h from each term. You can do this by factoring, or you can just see that there's an h in every term. That way we can cancel out. Normally we can't cancel out here because there's a plus sign, but because we know there's an h in every term, we can do that. And what we want to do is split this up into separate limits because we don't have limits rules for something that complicated. So limit h squared over h, that's h. 4h over h, we have an h that cancels out, so limit h approaches 0 of 4. And now we can substitute it in. This is just 0, and this is 4. Okay, and that's our final answer. If you have a lot of work on the page, you should box your final answer. Okay, you might have seen this before, but this is a definition. Piecewise functions are multiple functions in a partition domain. A domain that is divided up into not necessarily even-sized intervals. So, for example, we have absolute value function, the absolute value of x. It equals negative x when x is less than 0. It equals positive x when x is greater than 0. This should have an equal sign, greater than or equal. Okay, these are our functions. Remember, I'm abbreviating function with Fn. And these are our intervals. Okay, there's two partitions here. So we have other uses for limits. We can fill holes for continuity using piecewise functions. Or we can change a discontinuous function into a continuous function. For example, let's look at a discontinuous function first. We have g of x equals, we can say f of x when it does not equal plus or minus 1. And we could say that it's equal to 2.5 when x equals plus or minus 1. So this is a piecewise function because we have partitions. We're partitioning at a point, but it's still a partition. Okay, so it looks like this. There's a hole here and there's a jump here. So let's find the limit of this. So f of x at 1, we want to find that. So limit x approaches 1, x minus 1 over x squared minus 1 equals limit. What we want to do is factor. This is x minus 1 over x minus 1, x plus 1. Because this is fully factored, we can cancel out this term and this term. That leaves us with a 1. When we're canceling out factors, we're left with 1, not 0. Very important. When we're canceling out terms from plus or minus, that gives us 0. So limit x approaches 1. We have 1 over x plus 1. What we want to do is use our limit rules. You haven't learned this yet. We can't just substitute into something like this. We need to take the limit to just the variable. Okay, now we can substitute. 1 over 1 plus 1, that's 1/2. So this is 1/1/2. Okay, so this is a function with a jump discontinuity. We can redefine it if we want to make this a continuous function. We would say h of x equals, we could say f of x. Sorry, there should be commas here. X does not equal plus or minus 1, and we can make it 1/2 when x equals plus or minus 1. Okay, and that would be a continuous function. This one is a discontinuous function. So the limit is 1/2, but our point here is 2.5. And this is because the limit only considers a point near a value, not at the value. It's important. The limit is concerned about what happens when we get close to the value 1, not at the value 1. And it's important to note that if we go back up here and look at it, our previous example, we're looking at the tangent by going very close to 0. We can't go to 0 because if we go to 0, we're dividing by 0 here. And then the tangent would be undefined. But if we look at it getting closer and closer to 0, we know it's getting closer and closer to 4. So we wouldn't be able to calculate the tangent if we were looking at the value. So we want to look near the value. Okay, I mentioned limit properties before, and here they are. So these are the limit properties we have to use. If we're doing the limit as x approaches c of a constant value, it's just going to be the constant value because x has no bearing on what happens to a constant value. If we're looking at the limit as x approaches c of x, well, it's just going to be c. And if we're looking at it on a graph, y equals x. Okay, so it's just going to be that value. Okay, here's some limit theorems, and L, M, C, and K are all reals. Okay, so it's a real finite value. It's a finite value. It's not infinity, it has to be a finite value. So if we can find the limit as x approaches c of f of x equals to L, and if we can find the limit of x approaches c of g of x and it's equal to m, then we have the sum rule. The limit as x approaches c of f of x plus g of x is just equal to L plus m. Okay, and we have the same thing for difference. F of x minus g of x is L minus m. And the product rule. These are all expected. So if you can find the limits, you can add the limits together. And the product rule. So if we can find the limit of g of f of x, if we can find the limit of f of x and g of x, we can multiply them together, L times n. So this limit x approaches 1. I know this is simple, but it illustrates the problem. If we're doing x squared times x cubed, we can do the limit x approaches 1 of x squared times limit x approaches 1 of x cubed. Okay, this is very simple, but we're going to apply it to harder problems, but this is just to get you to understand. Okay, and then we have the constant multiplier rule. If we just take some constant multiplied by f, it's the same as k times L. And the quotient rule. So if we can find the limit of f and g, we can do L divided by m, provided that m does not equal 0. We can't divide by 0. This one's a little bit harder. We have a couple new variables, r and s. They have to be integers. Okay, so if we can find the limit as x approaches c of f of x, then we have L to the power of r divided by s. Okay, so if we have rs as integers, this is called a rational. Okay, so this is limited to rationals. It can't be an irrational. We can't use these rules on polynomials directly because this is called direct substitution, but we can use it on each term. Okay, so let's look at a slightly more difficult problem. And we have a cubed binomial, so we need to use the binomial expansion. Limit h approaches 0. And this is a constant of 1. Here's a constant of 1 as well. That makes it easy, so we use Pascal's triangle. And again, I'm going to rearrange it so that h comes first. H cubed plus 3h squared plus 3h plus 1 minus 1 cubed. And that's all over h. Okay, so the 1 cancels out with the minus 1. Now we have limit h cubed plus 3h squared plus 3h. All h approaches 0, and it's all over h. So h cubed divided by h is h squared, and I'm going to break it up into individual ones. H approaches 0 of h squared. And we cancel out an h, so we're going to have 3h plus limit h approaches 0, h plus limit h approaches 0, 3h over h, that just gives us 3. Okay, so technically here, we can plug in a 0. We're not going to trivialize this too much, but really this is limit h approaches 0 times limit h approaches 0 of h. That's a times. Okay, so we get 0 times 0. And again, technically, we have 3 times limit h approaches 0 of h. And we got 0 plus 3, and that's 3. Now, very important, when we're doing this, we should never be left with something over h. Because if we're left with something over h, we've done something wrong, because we're dividing by 0. The h in the denominator should cancel out. And if you haven't done that, it's incorrect. So let's put that down as a note. Not have any limit h approaches 0, any constant over h, because undefined. Okay, that's shorthand for because. Okay, next, we have one-sided limits. So a left-handed limit, we use a negative sign. And this is a superscript. It's not a C minus. Okay, so that's as x approaches C from the left. And if we put a superscript plus sign on the constant there, that's approaching from the right-hand side. And here's an example of where we need to use it. Okay, so limit as x approaches 2 from the left. Okay, here's 2, approaching it from the left. Again, we're not concerned about what the value is at 2, because at 2, it's equal to 3. But the limit, as we're approaching from the left, it's going to equal 1. Okay, and the limit as x approaches 2 from the right. So we're coming from this side to 2, and it's equal to 3. Even though f of 2 equals 3. Okay, and a two-sided limit. The limit as x approaches c of f of x equals L. And this is called if and only if. If and only if. The limit as x approaches c from the right of f of x equals L, and limit x approaches c from the left, f of x equals L. So if we have this, it means this. If we have this, it means this. So if and only if means it goes in both directions. So a lot of the functions that we have are continuous. So usually we need to do the two-sided limits when we have piecewise functions. For the previous example, we have limit x approaches 2 of f of x does not exist because limit x approaches 2 from the left of f of x equals 1. And this does not equal the limit x approaches 2 from the right, f of x equals 3. And another example, we'll take the limit of the absolute value function at 0 because the boundary of the partitions is at 0. So limit x approaches 0 from the left, absolute value of x equals limit x approaches 0 from the left. And from the left, we have this, okay, because that's less than 0. So we have negative x, and that equals negative limit x approaches 0 from the left of x, and that's just minus 0, and that's just 0. Limit x approaches 0 from the right, absolute value of x, equals limit x approaches 0 from the right, and that's just x, and that's just 0. Okay, so limit x approaches 0, So this is going to be two-sided equals 0 because the left and right are equal. Just so that you know the proper definitions, 0 minus negative x, 0 minus x, negative x. We have binary operators. Okay, that means it takes two parameters. That's this one, and it's also this one. Okay, so these are minus signs. This is a minus because it's binary. Unary operator means it's just one operator. It just takes one parameter, and this is a negative. Okay, so I try to be precise, but I'm not always there. But you should understand that when we have one parameter, negative x, we should be saying negative. It would be incorrect to say negative minus x or 0 negative x. This is 0 minus x. This is 0 minus negative x. So where the minus sign goes, you should call it by the correct term. Okay, limit theorems. These limit theorems will help you solve some of your homework problems. We're not proving these at this point. Proof will come later. But the limit as x approaches 0 of sine x over x, that's equal to 1. The limit as x approaches 0 of 1 minus cos x over x equals 0. And once we're confident that you understand all the limit rules, you'll be able to use direct substitution later on. On the test, be careful of when you can or cannot use direct substitution. Once we show that a function is continuous, we're allowed to use direct substitution. And that completes this lesson.